Hey everybody. Today we're going to do some Poisson regression in R. I'm going to be looking at the bike sharing dataset from the ISLR2 package. I've already loaded that up along with tidyverse, of course. The ISLR2 package is a bunch of datasets supporting the excellent book Introduction to Statistical Learning with Applications in R, which I highly recommend. I've pulled up the help file for the dataset, bike share, and you can get a little bit of information about what we are looking at here. It's a set containing hourly counts of bike rentals in 2011 in, I believe, Washington, D.C., United States, for their bike share system. We have information about the weather, season, whether or not it's a working day, obviously what time it is, and how many bikes were rented. The other thing I want to point out before we jump into this is that this data set originally comes from the, the UCI Machine Learning Repository. And this is worth a click. There's a lot of fun data sets there for exploration and learning. So check that out. Let's glimpse this data set. We've already loaded up tidyverse, so we have access to glimpse. Let's take a glimpse at bike share, see how this looks. All right, so we have 8,645 rows with 15 variables. So each one of these rows is going to be an hourly observation of things like temp and number of bikers. So I want to look at the bikers variable as my response. I'd like to explain how many rentals we're going to have, how many bike rentals we're going to have on the basis of some of these variables. And which ones of these really belong in the model is a very interesting question, and there's a lot to be said about that. I'm hoping to get to that in a little more depth in a future video. Today, I just want to look at a handful of these variables that seem fairly obviously important. I'm going to use temp, like what's the temperature that day. I'm going to use working day. Is it a day when people actually have to go to work, or can they just ride for pleasure? And then I'm going to use weather sit. And you can even just see from the first couple of observations here that this is describing like the situation of the weather. So in this case, we've got clear. There's also misty, cloudy, light rain, stuff like that. All right, so before I do anything else, I want to get a little bit of a visualization of this data to motivate why I want to do a Poisson regression and not, for instance, a linear regression, multiple linear regression. So let's get a ggplot using bike share. And on the y-axis, I know I'm going to want the bikers, my response variable. So I'm putting that first just because that's where my train of thought is. Now, I'm going to be using these three variables here, of which only one is really quantitative, temp. So let's put that on the x-axis. Notice that working day is coded as double, but really it's binary. It's true or false, zeros and ones. To start, I think I'm going to leave that out. I just want to scatter plot. And what I'm going to do is I'm going to facet it. And I'm going to facet it by weather sit. And there's no T in facet wrap. And let's just see how that looks to start. All right, so I'll need to zoom in on that for you because I'm pretty zoomed in here. All right, so we're getting what we want. I'm going to want to put some transparency on here. There's a lot of overplotting. I don't have a good sense of these plots right now. I'm also noticing that the heavy rain snow category here is not ideal. I'm not going to deal with that in this vid. That's another thing I would like to spend a little time on. Maybe recoding both light rain snow and heavy rain snow as just rain/snow. This category doesn't seem to be doing anything. I think the person that put this data set together probably forgot that they had it. I don't know. Maybe it's possible there's just one day where it rained and snowed heavily in that entire year, 1 hour, but I don't think so. All right, so let's put some transparency on here with alpha equals, I think 0.05 was good. And while I'm at it, I think I'll do a theme minimal. You know what? Actually, I think I'm going to do a theme set because I'm going to be doing a few visualizations here. So let's do theme set, theme minimal. That way I'll get theme minimal all the way through, regardless of whether I enter it or not into each plot. Okay, so we could go back and tinker with this and make this a little bit we could change this in several different ways. I do think I'm going to put in a tiny bit more, a bit less transparency here. Doesn't make a huge difference. Well, I don't know. So the main thing I want to point out here is that this is not really a great candidate for multiple linear regression. And there's at least two reasons for that are visible from this plot. First of all, a linear regression is going to predict some negative counts here for some of these values of the explanatory variables. You can imagine putting a line on top of here. It's going to get negative. And of course, counts for number of bike rentals can't ever be negative. So that's a reason that linear regression is not going to be ideal. Secondly, you can see that the variance is proportional to the explanatory variable here, to temp. As temp gets bigger, there's more spread in our data. In a linear regression model, the variance should be constant for all values of the explanatory variable or variables. So that assumption is violated. Not to say that you could not theoretically do a linear model here, just that it's not the right tool for the job. So I want to do some Poisson regression, which is intentionally created to model counts. By the way, let me just do a quick copy and paste here. I said I was also going to use the working day variable. So I'm going to do this exact same plot, but go back and change weather sit to working day, just to illustrate that we've got the same issues here. That there's more variance as temp goes up, and that if we were to try and draw a straight line on this, we would very likely get some negative predictions. Hey, also notice that temp here only goes from 0 to 1. Let's go back to this help file and figure out what's going on with that. It's worth noticing. So in the little data dictionary they provide, we can see that temp is normalized temperature in Celsius. So what they've done is they've taken the temperatures, which at minimum were -8 and at maximum were +39 on the centigrade scale, for that entire year. And then they've just put those on a 0 to 1 scale. And that's the sort of thing that would make a lot of sense if you were doing, for instance, a principal component analysis or certain other forms of machine learning. In our particular case, it's not going to be that helpful. If anything, it's going to make our model a little harder to interpret. But I'm not going to mess with that today. If you need to convert it back, you certainly can. All right, so before I actually build this model with those variables I mentioned, I have a couple slides I want to show talking a little bit about how I'm going to do this and how Poisson regression really works. So let's take a second and look at those. So as I mentioned, Poisson regression is used to model counts, like the number of bikes rented per hour in Washington, D.C. And the general form for the model is this. We are going to have a random component that is a Poisson distribution. That is, modeling counts where you have lambda representing the expected number of occurrences per unit time, in this case per hour. And then we have a systematic component where the right side is linear in all of the explanatory variables and the left-hand side is log of lambda. And the reason for that log is simply that it's going to take what by nature are positive values, those counts, and reconcile that with the fact that the right-hand side should be able to take on any value. And just broadly speaking, it's going to fit our graph very nicely. There's a lot that can be said about that natural log. That's called the link function for this generalized linear model. We're not going to get into any of those statistics here. The betas are going to be unknown coefficients that have to be estimated using sample data. And of course, we're going to do that using R in just a second. So the thing I really want to talk about here is that in this example, we have one quantitative variable, temp, which I'll represent as x1, and two categorical variables, working day and weather sit. And so I want to clearly state how we're going to encode those in our model for at least two reasons, one of which we'd like to understand what we're doing always. And two, we're going to get some code output from R in a second that's going to be in the form of a big table, and we want to make sure that we're able to interpret that properly to get the best results from our model. So let's start with working day. Working day is a binary variable. It's either true or false, so it's relatively easy to encode. we're going to take a variable x2, and we're going to let it be 0 if working day is false, and 1 if working day is true. So if you think about this in terms of the effect on this model that I have up here at the top, what's really going to end up happening is we're going to have two models. One for when working day is true, one when working day is not true. And if we were to visualize this, as we'll do a little bit later, we'll have two curves on our plot. For instance, one on each of those facets for the plot that we showed faceted by working day. Now, for weather sit, we have four possible levels: clear, cloudy, misty, light rain, snow, and heavy rain, snow. And so to encode this one categorical variable, we're going to need three indicator variables, three of these dummy variables. One saying whether it's cloudy or misty as a true-false, one whether there's light rain, snow as a true-false, and one whether there is heavy rain, snow as a true or false. And so if we take these three variables together, this encodes the weather sit variable completely. And here's a nice little summary table that I made for you. If the weather's clear, then all three of these indicator variables are 0. If it's cloudy, misty, x3 is 1 and the other two are 0, and so on. So overall, we're going to have this model. The natural log of the expected count, number of bikes being rented that hour, is going to be this linear function that's going to have all 5 of those variables that we just mentioned, as well as an intercept term. And I said I was going to encode those with the letters, or with the variable names x1 up to x5. So here it is written in a slightly more compact fashion. One other thing that's worth saying here is that natural log is invertible. So if we'd like, we can write our model like this. Lambda equals e to this linear model that we have here, the beta naught plus beta 1 x1, etc. All right, let's swipe back to R and actually fit this. Great. So we're going to save it as just model. I'm not going to be too creative with my names here. And the command we're going to use is glm. That's the same command that we would use if we were doing a logistic regression, for instance. We put the response variable first, that's bikers, and then the explanatory variables. We're going to explain it with temp, working day, and weather sit. We have to say what data set we're using, because right now R doesn't know where to look for temp, working day, and weather sit. So it's bike share. There it is. And we have to let R know what kind of generalized linear model we want with the family argument. And so it's family equals, quote, Poisson. There we go. And we can see what kind of output we get here with the summary command. So let's go ahead and do this. And I'll change over my window pane so you can see it hopefully a little bit more clearly. Okay, it doesn't look too bad. I'll render it in just a second, or I'll look at this in a slide in just a second to make it even more clear. So the thing I want to point out before I do that is just this coefficients table where they say estimate. So they've given us an intercept, and that's going to be exactly our beta naught. It's not technically an intercept for this if we were to draw this model on our plot, but it is that beta naught term. And then we have our coefficients for beta 1, beta 2, beta 3, and so on. So this is the coefficient sort of for the slope before the exponential happens for the temp. Working day is going to be the coefficient for the working day indicator variable. And I'll take a second and interpret those a bit more in just a second. So let's take a look at the slide I have for this that goes into some of these estimates and puts them into the model so we can see them explicitly all at once. By the way, what I've done to get this table is I've taken that same model object that we just looked at. I used the tidy function from the broom package, and then I piped that into the GT function, which gives me a nice table. Great tables. I have a vid on GT. I'll throw a link to that up top. I have also a vid on the broom package as well, but it's less relevant to what we're talking about here. So I'll put a link down in the comments or something. All right, so I basically just recreated the table that we were looking at a second ago when we were over in the RStudio console. And down here, I have just plugged in these coefficients literally into the version of the model that we were seeing here with the exponential on the right-hand side. And I've done a tiny bit of rounding, so just for the sake of the slide. So lambda equals e to the 3.89 plus 2.13x1 minus blah, 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 blah. Now, we have some natural interpretations of this. If I do a little bit of algebra, instead of having one big exponent separating out the exponentials with wherever I see a plus in the exponent, it's a product of the exponentials. I can write it like this. So when all of the explanatory variables are 0, x1, x2, x3, x4, x5, all of these exponentials here become 1. So lambda is e to the 3.89. And that gives us a really easy interpretation for beta naught for 3.89. When all of the variables are 0, which corresponds to the minimum recorded temperature, which, if you remember, was negative 9 degrees C, with 0 for each of the indicator variables, meaning that it's not a work day and the weather is clear, the expected number of bikers is e to the 3.89, or 48.9 bikers. In this case, that's a realistic interpretation of the beta naught. We should recognize that in a lot of instances, having all of the explanatory variables equal 0 doesn't actually make sense. It ends up being extrapolation. So while this is a good interpretation here, more broadly speaking, you want to be, I think, a bit more careful with that. For the coefficient beta 1, we can interpret it like this. For every additional unit of temp, the expected number of bikes increases by a factor of e to the 2.31. So I'm taking x1 to be 1 here. And that's a factor of 8.4. Now, in this case, that's a very large factor because the temps only go from 0 to 1. Remember, they're on that normalized scale. So that goes from the very minimum temperature observed to the very maximum temperature observed. If I were doing a slightly more detailed analysis on this, I think I might start by putting getting a column back in this data set where temp is actually in C, so that I could interpret this a little bit better. For every additional unit of temp, C. What's the factor by which the number of bikes increases? Similarly, for the other variables we have here, if x2 is 1, then that's going to tell us the change in the expected number of bikers when x2 goes from 0 to 1. That is when it is actually a working day. And, as you'd expect, the number of expected bikers decreases. Now, one interesting point here is that the number of expected bikers decreases by only 1%. It changes by a factor of 0.99. So whether or not it's a working day doesn't make a huge difference in the number of bikes that are rented. One reason might be that some people are using their bikes to commute. By the way, since I'm talking about that, let's go back and look at this table for working day 1 and contrast. The p-value is exceptionally small here. This is a statistically significant explainer of the number of bikes rented. However, the actual importance of this explanatory variable isn't that much. Knowing if it's a working day or not only changes your prediction for the number of bikes rented by about 1%. So that's an interesting contrast. Similarly, if the day is cloudy or misty, the number of bikers decreases by a factor of 0.96, so it drops by about 4%. If it's light rain or snow, it drops by about 35%. And heavy rain or snow, the interpretation we have here is that it drops by 52%, but remember, we only have one observation here, so I wouldn't put too much stock in that. All right, I think before I wrap up this vid, I want to make a model. I want to make a visualization or two to actually get this model, or one very much like it, as a plot. So let's do another ggplot. In fact, maybe I'll just start by copying and pasting the one I have, so you don't have to watch me type all of this. Great. Maybe I'll put the alpha back to 0.05. And I'm going to want to put a geom smooth in here. And I'll mess with this. I'll do other things. But to start, I just want to get a geom smooth. And I want method equals quote GLM. What's going on here with the method is it's literally going to be calling on this GLM function. In the same way as if we were doing a regression line, when we put method equals LM, it's literally calling on the LM function, the linear model. So method equals GLM. Let's see here. I don't want a standard error ribbon. That'll just make things noisier in this case. And I'm also not really doing a lot of inference today. And finally, I have to let R know what kind of GLM I want. I have to pass this family equals Poisson argument somehow. And the way we do that is with method.args and then as a list, because there could be more than one method arg. And I think that's all I need. Let's see how this comes out. Oops. All right, so something used incorrectly. Method equals GLM. Oh, wait, there's an extra point in the alpha. That's not even a problem with the GLM. It's a problem, or with the GLM smooth, it's a problem with the alpha. So let's zoom in on that. Okay, great. So right now I am only showing temp, working day, and bike rentals. I haven't shown the weather sit yet, but already you can see that this is looking like a realistic model. As temp increases, the number of bike rentals generally increases. You can also see that we have differences based on whether or not it's a working day. Let's also, just for the sake of completeness, let's put color in here. That's the other thing in our model, right? We're supposed to be also having weather sit in here. So let's have a color for weather sit. And if I'm putting in a color, I want to try and get something slightly more colorblind friendly with scale color brewer. Palette equals quote dark 2. I'm told that's a little better. All right, so now we actually have 6 different curves on our plot, sort of 6 different models here, reflecting the fact that we have several different levels to each of these categorical variables. All right, effectively we have 3 weather sit levels because heavy rain and snow isn't really being shown here. We have 2 levels for the working day variable. And now we can see that there are some differences here between these different groups. Now, there's still a bit of a to-do list here. There's lots of stuff that we could do better in this model. Certainly, I've looked at some interesting variables. They all came back as statistically significant, but a number of things that I could do differently, better, or in more depth. First of all, I did not do a training testing split on this. That's some standard practice if we're actually trying to compare and build effective models. I left out a lot of potentially very interesting variables. If I go back to this glimpse command, here, I didn't look at any of the time-sensitive variables, like hour. I know that time of day is going to matter. We're going to have a lot more bike rentals at 10 a.m. in the morning than, for instance, 4 a.m. at night, and so that's something. Similarly, the season might matter, humidity might matter, wind speed might matter. All of these things could be interesting. I mentioned about heavy rain and snow in my weather sit variable. I would like to go back and recode that, potentially fold it into light rain and snow and just have one factor level that says rain, snow, something like that. Another thing that I want to say for my to-do list is the number of rows, and this is the thing I'll close with. Here we have 8650 observations in our data set. But if you think about 365 days in a year and 24 hours in a day, I'll make a comment on this in my script, which I'll post to my GitHub as usual. That's hours in a year, 8760. But we only have 8,400 observations in this data set. And I did a little tiny bit of investigation in this, and it turns out that if you look at bikers, there's actually no zeros here. So whenever there was an hour where there was no bike rented, there's just not a row in here. And that potentially could change the model quite a bit if there's just no zeros in my Poisson regression model. Presumably, all of these predictions, all of these models that we're seeing here are a bit inflated. So for a more thorough analysis, I'd want to go in and actually insert some rows with some zeros in a thoughtful way to try and get a better model.